Welcome everyone to this session of our Proteus seminar series. Our speaker today is Daniel Sudarsky, and he will talk about a very interesting topic, of course, a central topic for the Proteus team. His talk is titled Connection Between the Problem of Time in Quantum Gravity and the Measurement Problem in Quantum Theory. So, Daniel, thank you very much for being here, and I'll leave it to you.
Thank you, Sylvia, for the kind invitation. Thank you, everybody, for being here. Let's hope you find this interesting. Okay, as Sylvia indicated, the topic of the talk will try to connect these two issues that should be very interesting. They're the subject of many research programs, each one of them individually, not so often together. Okay, so the plan of the talk is basically to review the problem of time in quantum gravity, why it appears, why it is there to start with. I'll try to do so from mainly conceptual perspective rather than focusing on the technical details, which are many, and technical mathematical complications, which are many. Then I want to review the quantum measurement problem. Probably most of you are familiar with them. If you are a physicist, perhaps you have not, been focusing on that for a while. I'm going to try to convince you that this problem is very, very serious, in particular in the kind of gravitational context in which I am going to describe it. And then I'm going to describe for you what is our approach to exploring the gravity-quantum interface. And that's not going to be a theory of quantum gravity on which I think probably should be the fundamental theory, but on which I tend to remain agnostic. In other words, I will not start by assuming that I know what the theory of quantum gravity is. And then I'm going to give you a possible clue of how a path to deal with the measurement problem could also be a path to deal with the problem of time. This is going to be just at the clue and intuitive level, because I'm not going to really propose for you a full-fledged theory of quantum gravity that is free of the problem of time. In other words, it's not that I'm going to give you the solution. I'm going just to show you that these two things may be linked together in perhaps a promising way. And then finally, and if there is time, I will also mention a possible connection with another subject that is quite interesting in connection with time, which is the problem of the arrow of time. If you want, the fact that we have a second law and that of thermodynamics and so forth. Okay, so let me start with GR and how the problem of time arises. In the classical setting of GR is, of course, described by Einstein's equations. The Einstein's equations, however, are not your standard type of equations in which which describe how certain variable evolves in time. Naturally, that's not the way it goes. But of course, it has something called an initial value formulation. In that formulation, we will represent the same content as the Einstein equations, but in a different manner, concentrating on Cauchy hypersurfaces that will be regarded as instants of time, the analogous of an instant of time. Of course, we know very well that there is no such a absolute notion, and we can choose those basically in a very rather arbitrary way, and that is going to play an important role in the discussion. So how does one go about that in the classical setting? One introduces some function called the time function, which is a mapping from the manifold to the real numbers in such a way that the hypersurface of constant value of this parameter is for every time a Cauchy hypersurface. Then one takes the unit normal, the vector, unit normal vector, which naturally is a time-like because the Cauchy surface is space-like, normalize, it's normalized appropriately, and with that one can generate what's called an induced metric, a three-metric Riemannian metric defined on the hypersurface. And then that variable, together with its instantaneous rate of change, basically 1/2 the Lie derivative of this metric, of this three metric in the normal direction, are taken to be the initial variables, if you want, the x and v's of the theories, the positions and velocities of the theories. And the theory is then going to be described as how this thing evolves. But of course, we need to, when we are going to talk about how these things evolve, we want to compute these all interesting objects, and in particular, the metric and the extrinsic curvature, compare them between two surfaces. And for that, we need to make an identification point by point among the two surfaces. And that is done using something called a vector field, TA, with certain characteristics. But the important thing is that each vector can be decomposed into a part that is normal to the first hypersurface, and then a part that is tangential to the surface. And that vector tells us which 2 points are going to be used in the comparison between the physical variables at the two hypersurfaces. But of course, the same way that this choice of time-like vector is arbitrary, well, so are the choices of these lapse and shift objects that are used to decompose it into a normal and tangential part. And then we will frame, as I said, the Einstein equations in terms of the evolution along this vector field of these x's and v's of the theory. It turns out that out of the 10 Einstein's equations, 4 of them, particularly the 4 corresponding to this projection, are not evolution type equations. They are more like, let's say, the Gauss equation in electrodynamics that doesn't relate time derivatives with the variables, but instead constrain the variables, your variables. In the case of electromagnetism, we know that the divergence of the electric field should be given by the charge density. Something similar happens in general relativity. The quantities, the dynamical quantities h and k cannot be specified freely as initial data. They must be constrained, must satisfy the constraint given by this expression. This is the three curvature of the spatial metric. This is the extrinsic curvature that we already introduced, and this would be the matter density, energy density associated with matter fields. Something similar occurs with the other three constraints that connect the extrinsic curvature and now the, if you want, momentum density in the matter fields. So here we have 4 equations, which are constraints equations. The other 6 equations are the equations that determine the real-time evolution of these variables. Once we have the theory expressed in that form, it's easy to just go to the Hamiltonian formulation. In other words, we're going from the x and v's to the x and p's. The momentum conjugate is going to be playing an important role. And it turns out that the momentum conjugate to the metric is a particular combination of this extrinsic curvature and also the metric. And now the same constraints will be written in terms of momentum and the three metric variable. Here I have written them in the case of vacuum where rho and j are 0, but of course in the case in which we would consider also matter fields. We would be use also a Hamiltonian formalism for those. We would have the corresponding expressions appearing here in the constraints written in terms of the fields, these matter fields, and their corresponding momentum conjugate. So the pairs or quadruples or entuples of data that satisfy the constraint generate the so-called physical phase space of the theory, in contrast with the generic pairs of those quantities, pairs or sets of pairs that generate the so-called kinematical space. Okay, so once we have the theory identify the variables and identify the possible initial or the possible canonical data, we have to write the Hamiltonian, and to write the Hamiltonian, we have to choose how we are going to, how are we interested in evolving, and that, sorry?
No, I think that somebody just had the microphone open, so.
Okay.
Sorry for that.
So we need to choose this evolution field, which, as I said, is described in terms of the lapse and shift. Once I choose the lapse and shift, their corresponding Hamiltonian takes this form, a combination of the constraints. And actually, if you vary this Hamiltonian, you obtain the equations of motion, which coincides with the equations of motion for that we had originally, Einstein's equations in the presence of matter in this case. One thing to observe is that the Hamiltonian actually vanishes on the physical phase space, but doesn't vanish on outside of it in the kinematical phase space. This could be perceived as perhaps a little bit counterintuitive. It is variations of the physical space that determine what goes on in the world. In other words, if I only concentrate in variations on the physical phase space, the variations of the Hamiltonian will be zero, because the Hamiltonian vanishes identically on phase space, on the physical phase space. Although this is a little bit counterintuitive, it's really what happens always when relying classically on an action principle. The classical path is, as you know, the extremum of the action. So it's the behavior outside of this actual classical physical trajectory that determines what is this physical trajectory. So at the beginning, one could be a little bit puzzled, but when one thinks about that, the problem is gone. Okay, after having a canonical quantization of the theory, we need now to proceed to the quantization, which is, is a prescription normally or very often done in the canonical setting. And in this case, as we are dealing with a theory that has constraints, in other words, the kinematical phase space differs from the physical phase space, it's very important that at the quantum level, we consider or restrict consideration to states that satisfy the quantum version of such constraints. And that may seem like, okay, you're just following a recipe blindly, but there are really very, very strong reasons to do so. The point is that the theory, even classically, must be recognized as being a redundant description of the physics in the following sense. The first clue that you are dealing with a redundant description of the physics is reflected by the fact that the theory as presented does not have a well-posed initial value formulation. In other words, the solution of the equations of motions is not unique. It is, however, unique up to diffeomorphisms. This is natural because the theory is supposed to describe the whole space-time, and it's being encoded in this canonical formulation by data on an arbitrary Cauchy hypersurface. The point, of course, is that the same solution, the same space-time, could have been encoded by data in any other Cauchy hypersurface. So we have here clearly a redundancy, right? I can give you the data that corresponds to a particular hypersurface, and that describes a space-time, and data chosen from another one, and that describes the same space-time. This is very different from what happens with ordinary field theory. For instance, Maxwell's theory. In that case, the background space, you have a fixed space time, a fixed background, and that provides structure external to the theory, and one can even take the foliation as given and fixed structure, and then consider evolution within that structure. So that the dynamical variable in that case can be thought as evolving from one hypersurface to the other in a well-defined manner. But even in Maxwell theory, say Maxwell theory in Minkowski spacetime, one has a redundancy, a type of redundancy in the characterization of the physical situation. It comes from a very different source, but it's again a redundancy, and it's called gauge invariance. We know that given a solution of Maxwell's equation, you can find another solution of Maxwell's equation by making a gauge transformation. And one may wonder if one is dealing with a redundancy or one is dealing with a symmetry, a real physical symmetry in the theory. That allows you to obtain a solution from another solution. I can start with a collection of particles and rotate this collection of particles and find another solution. That is a symmetry of the theory. One can distinguish between the two by precisely the issue of the initial value formulation. And here again, we have the following situation. You give me initial data for the Maxwell field at, say, t = 0, and you find any solution to that, to the equations of motion with that initial data, and I can find you another infinite number of other solutions, which are obtained simply by making a gauge transformation with the parameter, with the function psi that vanishes in the neighborhood of t. That means that the initial data will not be changed, but the rest of the solution will be changed. So here we see that we have this non-uniqueness. The redundancy, once the redundancy is recognized, once you recognize that the two solutions A prime and A really represent the same physics, then the problem is gone. The initial data provide a unique solution up to gauge transformation, and that can be proven. It's a theorem that applies to this theory. So the fact that the two solutions that differ by gauge transformation describe the same physics must be reflected at the quantum level by ensuring that the physical situation is uniquely characterized. And if we are going to characterize the physical state, by a quantum state, we'd better ensure that that quantum state reflects that redundancy or that ambiguity. If, for instance, we characterize the quantum state as a functional, in other words, as a mapping from configuration space into the complex, as would be the most straightforward way to generalize, let's say, the treatment of a collection of particles, mapping the configuration space into the complex. That's what the wave function does. In this case, would be a wave functional. We must ensure that the wave function acting on two configurations that differ by a gauge transformation gives exactly the same result. That is a consistency requirement for the state to make sense. It would be you would have a meaningless theory if things depended on how you happen to characterize the same physical situation. That means, this condition means that at the differential level, the generator that acts as a generator of infinitesimal gauge transformations must vanish when acting on the physical states. Of course, a finite gauge transformation will be obtained by exponentiating expression exponentiating the generator of the gauge transformations. So it better be that the generator of gauge transformation vanishes. And in this case, the generator of the gauge transformation turns out to be the divergence of the electric field viewed as an operator, of course. And then the constraint equation that we will have is this equation, is the so-called gauge constraint, which might be derived directly from the action on the classical level, from Maxwell's theory, by consideration of the variation of the action with respect to the variable A0, which happens to become a Lagrange multiplier. This is very typical of this kind of situation. So we see that there are very, very strong reasons for demanding that the physical states be invariant under this redundancy that is present of the theory. In gravitation, we have the precise similar case. For gravity.
Sorry, can I ask a question?
Sure.
If it's a clarificatory question, yes.
Yes, it is. You're asking that the states be invariant for gauge transformations, but usually it's the probabilities and not the states, right? So
well, you want
normally
people want this to be, to preserve all amplitudes, and you're right. You could have in principle some phase, but then there are theorems limiting exactly what this phase could be and so forth. Let me not get into those.
Okay, thanks.
Yes.
Thank you.
Yeah. Okay, the point is that here we have precisely the same situation. As we said, we had a redundancy in this theory, and then we need to ensure that whether the theory is vacuum gravity or gravity connected with coupled with other fields, we need to ensure that the physical states are invariant under diffeomorphism, or in other words, are annihilated by the constraints. So these are the corresponding form of the quantum constraints that we encounter classically already. In this case, the lapse and shift will play the role of the Lagrange multipliers that the scalar potential played in the Maxwell case. Okay, once we have this setting, we are led directly to the problem of time. So what's the problem of time in canonical quantum gravity? The point is that if we now want to contemplate for any choice of lapse and shift the corresponding evolution of the quantum state, the Schrödinger evolution, we would write a Schrödinger-like equation where the Hamiltonian is now this object, and the wave and our wave function is a wave functional of the canonical variable of the configuration space. The other canonical variables will be, of course, written in terms of functional derivatives, in the same way that the momentum is the derivative with I times the derivative with respect to the configuration space to ensure the canonical commutation relations. But then the equation tells us automatically that since the Hamiltonian is just a combination of constraints, and the constraints annihilate the wave function, if the wave function is physical, then we have that the evolution of this Schrödinger equation becomes trivial. The equation does not evolve. Nothing changes from hypersurface to hypersurface, and then no notion of time seems to remain at all. The problem is, of course, very well known, and it has a long history. Relatively recent, well, not so recent, but all classical reviews by Kukash or Isham classify the approaches people have employed to deal with this. Of course, there has been always, people working hard and trying to figure out ways to deal with this serious problem. And there are broadly three classes of approaches. There may be more, but I'm going to focus on the three that they describe. The first approach is to try to identify before quantization some time variable, something that could play the time variable, and then to obtain to obtain something like a Schrodinger equation, not with respect to this the parameter t that I introduced but with respect to this other combination of the physical quantities that we are imagining playing the role of a time variable. A second approach is to first quantize, impose the constraints on the physical states, including this so-called Wheeler-DeWitt equation. The Wheeler-DeWitt equation is, by the way, this first constraint. And then to try to identify something that plays the role of times. Find solutions to the Wheeler-DeWitt equations on the form, for instance, of a functional of the trimetric and, let's say, a scalar field, and then take the wave function and think of it as providing us conditional amplitudes or providing the effective wave function for the metric variable when the other variable, let's say this classical field, takes a given value. Okay, and the third approach is to proceed as before, but without really trying to find a generic object that will always play a variable, but try to provide a coherent interpretation, a probabilistic interpretation about this wave function without making reference to any notion of time, that is thinking of things like finding the particular, the conditional probabilities for results A on observable A given B, or given that B took place, something like a consistent histories type approach, or probably a more general many world type interpretation would probably go along with best with this type of configurations. However, it is a fact that none of this approach has become widely accepted and are not recognized as fully satisfactory solutions. Every researcher that focuses on one, of course, is going to be very excited about his or her approach, but none of them has managed to convince the community at large. And there's various objections that have been raised. Let me do that very, very quickly. The first one is, okay, you make this choice. If I made a different choice, would I obtain somehow equivalent physics? That's a big question that should worry whoever advocates one of the first approach. Second, in the second approach, if one finds something that will play the role of time, one would expect that after I have the theory and I start making the appropriate considering appropriate limits and appropriate approximations, I should be able to connect to non-relativistic quantum mechanics. And there, that object that I identified as the time should continue to play a role of time. However, there are general results that indicate the impossibility of constructing a time operator with the desired behavior. In other words, ensuring that, quote unquote, it always flows forward in time or something like that. That's impossible if the spectrum of the Hamiltonian is bounded from below. This is a result of Wald and Unruh in 1989 that, in my view, throws a bucket of cold water on this approach, at least if one wants to consider it broadly and generically, and not perhaps limited to very short periods or short regimes where these global impossibilities will perhaps be avoided. And moreover, the true observables of the theory, the thing that we wanted to be the time would normally want to be a true observable, are required to be gauge invariant, and then they commute with the Hamiltonian, and thus they become constants of motion, which seems to be problematic. And moreover, they are generically very hard to find. In arbitrary situations in which you don't have a lot of symmetry, these are very hard to find. Sometimes in what so-called mini superspace models, in which you apply, the theory to something like homogeneous and isotropic universes, and you describe everything in terms of just a couple of variables, you can find something that seems to serve, that could serve, but it's very hard to see this being a general acceptable solution. So in fact, Isham's 1992 review ends concluding that with the following quote, and I want to make it, to read it here. Therefore, I feel that it's correct to say that the problems encountered in unraveling the concept of time in quantum gravity are grounded in a fundamental inconsistency between the basic conceptual frameworks of quantum theory and general relativity. In other words, it doesn't regard this as a technical problem, but some fundamental inconsistency. Okay, so now comes what I would like to say about the subject and the approach I would like to. The first thing to realize is that it's very hard to do physics without having a space-time framework given, and doing so while trying to adopt a very clear and precise view about quantum theory makes things even harder. And this, in my view, leads to the discussions on the subject becoming, fraught with confusion. For instance, in the previous statement, we said, this is the wave function of, it will allow me to compute the amplitude of this variable when this other variable takes a value. Why should that other variable take a value? We don't know that. What is the scheme in which things take a value? Normally, things take a value in quantum mechanics if you measure them. But then, of course, all this is connected with a tendency to avoid, facing or taking a very clear stand about what I regard as the elephant in the room, the M problem, the measurement problem, or the reality problem in quantum theory. Well, which you all know is a very serious conceptual difficulty in the theory that sometimes, becomes has concrete and practical implications. Not so for the physicist in the lab that is doing an experiment. He knows when he's doing a measurement, what he's measuring, and so forth. But the problem becomes very, very serious when you want to apply the theory beyond that realm and go, let's say, to cosmology or talk about black holes and things of that sort, which is precisely what we are going to do. Okay, so now we go to the third subject. How do we approach the exploration of quantum theory and gravitation? We will do so in what's called a top-bottom approach. The usual bottom-up approach, one starts by assuming one has at hand the fundamental theory of quantum gravity, and then with that fundamental theory at hand, one tries to work hard to connect with the interesting subjects of cosmology and black hole. The top-bottom approach that we favor does the opposite. It pushes existing theory, that is general relativity and quantum field theory in curved spacetime, into realms where it starts facing problems, looking for hints about possible modifications that could serve as clues about the nature of the more fundamental theory. Okay, so as I said, the idea is to put GR together with quantum field theory. GR, of course, this means, of course, a semi-classical treatment because we are not quantizing at this level GR. Now, why could this be useful concerning the problem of time in quantum gravity? Well, here Isham again tells us, if the concept of time should emerge at the effective phenomenological level from something very different from just the standard canonical quantization of general relativity, it would be very important to understand what this new framework, what is new in this framework, And in particular, how does it appear in the context of something like semi-classical gravity? And this is precisely what we are going to try to do. So we are going to view semi-classical gravity not as a fundamental theory, but perhaps together with some adjustments as a point lying in the path connecting the fundamental theory, whatever it is, to what we know to be the very successful description that we have, tested and experimented with, that is classical GR. You expect the fundamental theory to reduce to classical GR at certain point, and there is going to be a set of approximations and caveats when this is possible, but in that line, there will be a point in which we expect to encounter a semi-classical gravity. And we will try to stick with a clear, although provisional ontological posture. Since we're describing space-time in classical terms, which we expect to be a good approximation if we don't reach Planck scale curvatures and fluctuations are not too large, and this needs to be defined more precisely. And quantum mechanics and the matter is going to be described quantum mechanically in terms of quantum field theory in curved space-time. It's very natural to say that the local variables or the fundamental local variable of the theory is what restricts the curvature of space-time, the thing appearing in the right-hand side of Einstein equations, namely in this case would be the expectation value of the energy momentum tensor. Here we face a difficulty. In a recent work with Tim Motley and Elias Ocon, we offer very strong arguments indicating that all reasonable approaches to the M problem, the measurement problem, the ontology problem in quantum theory, lead to violations of conservation of energy, and more precisely of conservation of the validity of zero vanishing divergence of the energy momentum tensor. So whatever we do, we will have to deal with this problem. The scheme is provisional because we expect, of course, something dramatically different may be needed in a theory in which space-time itself is described quantum mechanically, and probably our current notions of space-time would become emergent. And regarding the measurement problem, we will focus on one of the approaches to its solution that is called spontaneous collapse theories. There is a lot of work on this from Philip Pearl, Gerald D. Rimini Weber, Yossi Penrose, etc. There's certain advances recently making proposals that seem to be compatible with special relativity. Let me not get too much into that. The basic idea of these theories is to unify the standard unitary evolution with the reduction postulate, adding terms that will, make the two. And I will show you one particular form of this theory. This theory has addresses the measurement problem successfully, and is empirically viable, at least in non-relativistic regimes in the general sense. So, as I said, the ontology will be centered on this expectation value, where one should also specify, okay, on which state we will compute this quantity. Let me not get too much into that. But it's not to be regarded as an average, but the actual, ontologically present matter that is curving the space-time when the matter fields are described by those conditions. There is, of course, a wider discussion regarding the time in the problem of time in quantum theory. Let me not go into there because we are running out of time. So let me present to you one of those spontaneous collapse theories. If you haven't met that, the theory is called the CSL theory, continuous spontaneous localization, and is due to Philip Pearl. And the theory is specified by a modified Schrödinger equation whose solution has this form. So you have the first standard part that is controlled by the Hamiltonian operator, and a new part that is associated with various objects. that appear here. One is a coupling constant that tells you how strong these deviations are, lambda. Another one is a stochastic function of time. And the third object is the collapse operator, which indicates towards which type of states does the theory tend to drive any arbitrary initial state. Moreover, since this evolution is now not unitary, you need a new law of probabilities. The law of probabilities is given by this expression number 2. Let me not get into details. The point is that it's a new law of computing probability. You don't compute probabilities as before. In the non-relativistic context, this operator A was taken to be some sort of smeared position operator at certain scale. Here, the requirements is that the lambda should be small enough not to conflict with precision test of quantum mechanics at the subatomic physics scale, but large enough to ensure the rapid localization of macro objects. And with the suggested value of this parameter was taken to be of the order of 10 to the minus 16 seconds to the minus 1, or a few times in the, occurring, a typical collapse occurring, in average, a collapse occurring in this time scale. Okay. The theory actually is being experimentally tested. Some very, very simple version of the theory seems to be ruled out by a recent experiment. But of course, we don't have yet a theory that is fully compatible with general relativity. Of course, we all don't have a workable quantum theory of gravitation either. But in order to take matter seriously, we should define, even at the effective level of semi-classical gravity, what will we do with the non-conservation of energy momentum tensor? Okay, so for that we have developed a formalism which is inspired a little bit by, say, hydrodynamics, where we have a wonderful equation, the Navier-Stokes equation. Works very well in many circumstances, but we know it's not a fundamental equation. It's not the fundamental equation because the fluids are not really, continuous fluids. We know they are made out of molecules and so forth. And then it's not surprising the theory breaks down every once in a while. For example, when a wave breaks in the beach, a wave of in the ocean breaks on the beach, the equations fail terribly. And we will then look at semi-classical gravity as having the same thing. The theory that I'm going to describe in a moment is supposed to be valid most of the time, except when the collapses occur. Okay, so what is this semi-classical setting? Is basically the construction of a quantum field theory on a given space-time, plus the requirement that the state of the matter field be such that the expectation value of the energy momentum tensor of that construction in that state coincides with the Einstein tensor of the metric. Okay, so this is a self-referential equation. The construction of the quantum field theory depends on the space-time metric, but the space-time metric depends on the choice of the state, etc., etc. When a collapse occurs, there would be a transition from one of these configurations to another one, and we have worked to show how this thing can be done. Okay, so now very quickly jump to applications. One of the first applications is cosmic inflation. Cosmic inflation is now considered as a basic aspect of modern cosmology, and one of its most successful aspects is its supposed capacity or ability to account for the emergence of the seeds of quantum structure in the universe out of quantum fluctuations with the correct spectrum. The theory is remarkably successful at the quantitative level, but at the conceptual level, the theory is seriously problematic and not satisfactory. This should come as no surprise because, as John Bell pointed out, in quantum mechanics for cosmologists, once one goes into cosmology, there is a serious problem. he says rhetorically, was the world function waiting to jump for thousands of millions of years until a single cell living creature appear, or did it have to wait a bit longer for a more qualified measure with a PhD? Actually, in this account, things becomes even worse, because in cosmology, we need structure to appear before any living creature, much less a qualified astronomer with a PhD, could ever appear. We are consequence of the fact that the universe contains structure, and we therefore cannot be part of the story of how structure appear. And on the other hand, according to the inflationary account, the state of the quantum field and of the perturbations is described by something called the Banach-Davis vacuum, which is completely homogeneous and isotropic. The state is 100% homogeneous and isotropic, and nevertheless, people say about it, its quantum fluctuations, or more precisely, the quantum uncertainties, account for the emergence of structure. But quantum fluctuations are not statistical fluctuations. They are not things that happen. They tell you about what would happen if you decide to measure certain quantity multiple times, and what would be the dispersion of things if you measure. But if you don't measure, the state remains the same. And if the state was symmetric, it will remain symmetric forever, according to the standard dynamics. So the dynamics of the theory doesn't break the homogeneity and isotropy of the state. One can choose, for instance, the homogeneity of the state by simply applying a displacement operator on the state and seeing that the state becomes invariant. But at the end, the theory, the situation we need to describe is a universe filled with galaxies, star planets, and so, which is clearly not satisfying this condition. How is that happening if the symmetries, if the dynamics doesn't break the symmetries, and there is nobody to measure? Okay, it turns out that suitable adaptations of these collapse theories and for appropriate choices of the collapse operator allows you to deal with the problem and to obtain the correct spectrum. This, if you want to read about one particular version of this is a paper in which we show that. Interestingly enough, as a bonus, the approach we adopted, semi-classical gravity plus collapse theories, can be made to make the correct predictions for the spectrum of scalar perturbations. Those are the ones that account for the inhomogeneities and anisotropies that lead to galaxies and so forth, but makes very different predictions regarding the tensor spectrum or the so-called gravity waves, and naturally accounts for the fact that we have not seen them. Okay, this is in this paper, reassessing modes. So we've seen the first, if you want, successful application of the approach. Black hole information problem, also I'm going to say very, very quickly. The first thing one needs to realize that there is really no black hole information problem if one uses the picture that I have here. Why not? Because in this picture, there is this boundary of space-time that, reflects the fact that in this space-time, there are not really Cauchy hypersurfaces. And you can expect unitary evolution, even in standard quantum theory, in the absence of measurements, only if you are comparing the full data to full data, and full data would require a Cauchy hypersurface, which is not. So it's only if quantum gravity cures the singularity and removes the need for the additional space-time boundary that one really has an issue with the black hole information problem. That is discussed in this paper. But in theories with spontaneous collapse, departures from unitary evolution are present in general, and we were led to consider, this scheme in which the two types of departures from unitarity, the one that is associated with black hole evaporation and the one that is associated with collapse theories, are really one. This has been initially proposed in this paper, and then actual calculations, in relatively simplistic models have been done in these papers. One thing that we learn out of this exercise is that if we want to ensure that all information inside the black hole, and in particular the entanglement between the exterior and interior degrees of freedom in the quantum fields, are to be erased in the finite time to to the region where quantum gravity would take place, or the region where normally the singularity is thought to be located, we need to ensure that the collapse theory becomes much more rapid and much more effective than normally is supposed to be. And that can be done by assuming that the collapse, the parameter controlling the collapse, is not really a constant, but depends on, for instance, some curvature scalars. In particular, we were very attracted to the idea that the Weil curvature scalar is the one that is dominant, because it will be present even in vacuum. So if you have something like this, you can ensure that the theory achieves in a finite time to in a relatively finite time available to reach the singularity, what ordinary collapse theories, or what the ordinary versions achieve in the very long term, or even in asymptotically. That is, to drive the state towards one of the eigenstates of the collapse operators. So the picture one has is a picture like this, in which one starting in the past in sigma 1 with a pure state, and by the time one reaches sigma 3, one has erased most of the information before going to the quantum gravity region, and then one describes what is the final state in sigma 2, which turns out to be just radiation, thermal radiation, plus a vacuum to the future, Minkowski vacuum to the future of that region. Information is lost as a result of the general quantum evolution, which has this collapse feature, which is amplified in the region before arriving to sigma 3, and there is absolutely nothing paradoxical. Okay, so now we finally reach the point of the clue. Since this talk has been about there being no time, I'm going to be a little bit loose with the use of time. That is, I cannot be running out of time if there is no time. Okay, so we have argued that in canonical quantum gravity, the problem can be traced to this diffeomorphism invariance together with the quantum treatment of the gravitational matter degrees of freedom, which imply that we have to regard states associated with different hypersurfaces as encoding the same information. And that means that you can have no evolution. Dynamicas collapse theories remove this basic feature of standard quantum theory, because the deterministic and unitary evolution that we saw is at the core of the problem is basically modified, and things do start to happen simply because of these spontaneous collapses that this theory introduces. So what forced us to associate the same state to different hypersurfaces is not longer present. This feature, once this feature is removed, and we have a certain hypersurface sigma prime to the future of another hypersurface sigma, we can say that the state at the two differ by the effect of the collapse that took place in between the two. This can be regarded schematically. Of course, I don't have concrete expressions to write to that. But if we look at the equation of motion that would be satisfied by the now modified type of evolution that contains not just the Hamiltonian, but the stochastic terms, we would have the evolution of the Schrodinger, the modified Schrodinger evolution be controlled by the Hamiltonian part, which continues to vanish, plus this extra term that depends on stochastic, on the physical variables, but also on stochastic terms, which will not in general vanishes. This might describe heuristically as representing the things that happen between the two hypersurfaces. In that situation, we do have change in the quantum state, and therefore we will have time. The idea is now given by these hypersurfaces would have been considered as characterized by the same state. Nothing has happened, but now due to the collapses, the blue collapses that occur between sigma 1 and sigma 2, the state in sigma 2 will be different, and so would be the state in sigma 3 differ from the state in sigma 2. Okay, so that is the proposed connection between collapse theories and what we think is the required emergence of time in a theory in which there would be quantum gravity, at least in the description at the semi-classical level that Isham told us would be interesting to understand. Okay, so if I have, how am I doing in time?
Well, actually, in principle, time is over, but of course, since it's very intriguing, the topic of the entropic error of time, I would suggest.
Okay, it's just two transparencies.
Yes, please
Two
go ahead.
transparencies, and we started a little bit late also. Okay, okay, so here is the other part of the story. It is well known that in order to account in the context of time reversal or time of a theory based on time reversal invariant laws of physics, which are precisely speaking, they are not there. There is a particular aspect of the standard model that is not exactly time reversal invariant, but is not supposed to play a very important role. But if the laws of physics were precisely time invariant and there was and this other thing doesn't play a role, we need to account, in order to account for the error of time, we need to have a very special initial state of the universe. Roger Penrose has proposed that such demand can take the form that the initial condition would be a state, or we restrict the state to be one which would have vanishing Weyl curvature, while allowing for arbitrary large values of the scalar or Riemann, or Ricci curvatures scalar. The arguments are motivated by his observation that at late times, the entropy of the universe seems to be concentrated in the many black holes, and especially in the very large black holes that seem to be ubiquitous in our universe now. And there are, on the other hand, no indications that something like white holes, the time reversal of a black hole, were present in the early universe in any form or shape, despite the very large curvatures that are associated with that regime. He describes this in terms of this picture. The right-hand picture is what he would say it would be a normal or a generic type of universe, starting in a condition with many white holes and singularities of this form, and then forming again, expanding perhaps, and then forming black holes at very late times. But our universe seems to be not of that form. It seems to be better described by something like the left-hand picture, where black holes do appear at late times, but the early time is rather pristine, except for, of course, this regime in which the scalar curvatures go to infinity, but without Weyl curvature. And he thinks of this as a kind of initial condition law, which would be very different from all other laws of physics that we have encountered before, which are generically, evolution type laws. However, the considerations involving the measurement problem and the origin of structure, and in particular the black hole information, so-called paradox that we discussed about, offer a very interesting possibility. Let's look again at the CSL evolution equation. And we see that this CSL evolution equation is controlled by two terms: the Hamiltonian term, which seems to be dominant most of the time, and this extra deviation of evolution, which is, on the one hand, subdominant in most situations. It will affect, importantly, experiments with a few particles and what we normally call the quantum part of the evolution, and in particular when something like like a measurement needs to be accounted for, or something measurement like it needs to be accounted for. But these terms are normally supposed to be small. But now what happens if so as I said, in generic circumstances, the evolution will be given by the first term. The second thing would be subdominant. However, if lambda grows with the Weyl curvature, then in regimes where Weyl curvature is large, the evolution will be completely dominated by the second term, and that will be completely random evolution, because that evolution is a very important central role in that evolution is played by this stochastic function, in this case of time, but in general of time and space. And then we will have a completely disorderly evolution. And then we can envision a universe which had generically very large values of the Weyl curvature, and it would be evolving randomly, jumping from one such configuration to another for a very long and indefinitely large lapse of time. And this here, of course, until at some point, and just by chance, it went to a state of almost vanishing W. In that case, if that was the case, at that point, the ordinary Hamiltonian evolution will take over and will become dominant, and the universe will start evolving in a orderly way. In particular, it could start expanding. It could start expanding. Eventually, structure would form in that universe, again, out of the small corrections caused by the collapse that would grow due to gravitational instabilities, blah, blah, blah. Creatures will appear. Some of them will start investigating, and when they look at their universe and they look backwards, they will be able to pinpoint to a point, to what they would regard as initial state, as one having very low Weyl curvature. Why? Because it's only when the low Weyl curvature or vanishing like Weyl curvature occur that the orderly universe could have arisen. So this would be basically a dynamical realization of Penrose's proposal in a unified scheme, accounting for various other problems as I have described. This idea is proposed in this paper, again with Elias Ocon, and and then let me finish here saying that the program, the general program, has more potential. Apparently, we can deal with eternal inflation. This is a paper under work. Anomalous low power at low L's in inflation. There is a lot of work ahead. I like to cite at this point Sir Francis Bacon, that concerning the general scientific enterprises, tells us truth emerges more readily from error than from confusion. It means that if you make a theory and your theory has an error, but you're very clear about what you are considering and what you are proposing, eventually you will find that the theory is an error, and at least you will learn that you need to fix that error. But if you work without very clear hypothesis and without being very precise about what you're assuming, then confusion will prevent you from learning anything. So I believe that ignoring the measurement problem in the application to quantum theory to generic situations beyond, particularly those beyond the lab, could be a source of serious confusion, and I encourage you to not ignore it if you can. Thank you very much.
Okay, so thank you very much, Daniel, for your talk. Actually, I have a follow-up because this afternoon I was listening to Penrose talk on an online conference, and of course I recognize the reasons why you think that your work matches, so to speak, what he's suggesting. But my question then is, how do we reconcile his position with regard to cosmology and his cosmological model with the idea of eternal inflation, for example, that you suggest here having,
Yeah, well, I of course emphasize the points of coincidence, but there are many points in which we don't coincide. Roger Penrose is not very fond of inflation. He has some serious criticism to the inflationary program in general. I share some of his concerns, although I cannot take myself to dismiss it completely, because there seems to be something there in the fact that you have this very exquisite match of literally thousands of data points on the predicted spectrum that coincide with the with observations. So I think something must be there. And then he has this Roger has this general idea of how to account for the low Weyl curvature in a different way with his conformal cyclic cosmology, which, to be really frank, I don't fully understand precisely how that works
well,
yeah.
indeed, there were a lot of questions to him, but I had to skip the discussions because we had our seminar, so it's a pity, because I don't know what he replied to the people that were asking precisely these questions to him. Though I think that there are some motivations that are related to some implications of Weyl spinors. So it's really something that he can motivate on that ground. But I don't want to, steal time to other people right now. So if there are questions, please raise your hands. And I don't know if there are people in the audience that want to ask questions to our speaker. Yeah. So Alvaro.
Thank you for the talk. It was very interesting. Sorry if my computer makes noises. I hope you can hear me. So I have a question about the motivation of discussing with the problem of time, because you were saying that because of diffeomorphism invariance, we say that the state of the world now is equivalent to the state of the world tomorrow, and therefore we get to this contradiction when we go to quantum theory because we love it, evolution. But in a sense, it is not surprising that we get this result if we are thinking that the state of the world today is in some sense equivalent to the state of the world tomorrow. So for me, from the 3+1 perspective, they are not equivalent. They are different physical states because they represent different ways the world are at this moment. And if we want to take a different perspective in the quantum theory, then we'll need to change the way quantum theory works. But it also works as in this picture of evolution. And then I think that the states should be associated with a time slice. And from that perspective, I cannot see that the state of the world today is equivalent to the state of the world tomorrow because they are different.
Okay, let me clarify. I'm not claiming that the state of the world today is the same state as the world. No, the point is, if you follow the canonical rules and you apply them, you are led in that way. And my point was to try to clarify why you are led in that way. It's not just a mathematical coincidence. There are conceptual things that when you put them together, you are led into that situation. And of course, I know that the word yesterday was not the same as the word today. I only need to look at the mirror, and we need to account for that. But it seems that if we apply the laws as we apply them, we are taking into that direction. So what to do? But the point here is that we already know, even before I look at the problem of time, even before I look at all these problems, to take quantum theory and stick just with the unitary evolution is not really a viable position. Is not really a viable position, right? Because I mean, we have, for instance, this result of let me say, there is this relatively well-known result. I don't know if everybody knows it, but this is a result by team modeling which says the following: the following three statements cannot be consistently kept simultaneously or argued for simultaneously. Number one, the wave function is a complete description of the physical situation, of the physical state of the world. Number two, the evolution is always given by the Schrödinger equation. And number three, concrete experiments, specific experiments produce specific results. You have to give up one of these three. Giving up the first one takes you into the realm of hidden variables, Bohmian mechanics type of things. When you say this, there is more to the physics than what is encoded in the states. Okay, that's one part. Part number two, you need to add something like that deviates from Schrödinger equation. That's in Copenhagen type of story, you have the collapse of the wave function. But in that story, the things are complicated and obscure because nobody tells you what is a measurement, who is an observer. It needs to be conscious. Well, you get into a whole bunch of things. You know, people that say that every interaction counts as a measurement, well, of course they cannot, that doesn't work, because if you had that, you wouldn't have interferometry, because your photon going this way and going that way interacts with mirrors, and then if that was a measurement, there would be no interference experience. So that doesn't go either. So you need to, if you're going to go that second way, the reasonable way to do it is with spontaneous collapse here. And then there is the third part, which is, you know, many worlds interpretation, consistent histories. Consistent histories has very, very, very serious problems. And many worlds in also has some issues. You know, people don't know really how to make room for probabilities, in particular in the absence of beings that are, you know, so many of the stories try to make it as a practical usage by intelligence beings. And what am I going to do with the early universe where there are no practical beings that use their intelligence? What probabilities am I going to talk about then, and how am I going to account for the distribution of the emergence of structure, etc. So, in other words, we know that we have this problem with the quantum theory itself. And no wonder that if you put them under the rug and hide it under the table, okay, we're going to find problems creeping up in another way. And in my view, the problem of time is one particular instance of that creeping up of the problem, because you hid it under the table and you didn't face it.
Yeah, okay, but that may be, but
no, well, that's the argument. I mean, this is the argument, right? Yes.
But it may be completely unrelated. Like, so sure, like for sure, you need to have a clear picture of what is a measurement, what's quantum theory about. But maybe the problem of time is independent of how you solve the measurement problem.
Well, not if I am right? Look, I give you an example in which I choose a particular solution, which happens to have seeds for possible resolutions. Actually, I should say, and I should acknowledge that people that work in the Bohmian approach have also a solution of time. They also have a solution for a problem of time. That's not the one I advocate, but okay. But I recognize they do.
Can I, Silvia, I don't know if someone else wants to ask for.
Yes, for now, nobody else raised their hand, so you can go.
Okay, let me then ask you something different. In your solution of the problem of time, you have some collapses, and then you have the geometry of space jumping from one state to another, something like that. But in between collapses, the thing, the state still in the satisfying the constraints, so there is no evolution. There is just the things will be still until another collapse happens, and then things will remain still until another collapse happens, and so on and so forth.
Yeah.
This
time would be in this picture. Time would be the cumulative effect of collapses. Of course, in the descriptions that I have done, and in the CS, in our formalism that we have treated with individual collapses, and that's the way that is easier to think. But the theory in which I gave you, that's called continuous spontaneous localization, collapses are happening continuously, like in a Brownian motion type of thing. Actually, they are supposed to be controlled by a Wiener type process. So it's things happen, like micro collapses that don't really localize the thing fully, but move it in the state a little bit towards increased localization, are happening all the time. And that would also count for this time. Of course, that the formalism to do that is much harder, because, you know, the formalism that I described for you, in which we connect two semi-classical self-consistent configurations through one collapse, this is very, very complicated, extremely complicated. We just published a paper on that. It's like 70 pages long. It involves, you know, how to deal with the renormalization of the energy momentum tensor when you only have data on an hypersurface, and all sorts of complications. And that is one single collapse. And now if I'm going to put, you know, a continuous of collapses, things are going to become very, very messy. I will have to do some process of, you know, discretization and taking the limit to a continuum limit and something like that is well beyond what we are able to do now. As I told you, our recent paper on the subject is just deals with one.
Yeah, but the point where I was trying to get at was that
no, but you're completely right. If collapses are discrete, then in between the collapses I have a problem of time.
Yeah, that's fine. But the point I was trying to get at was that when you have a collapse model for a particle, something like that, and you want to have like a classical limit, what is driving mostly the dynamics is the Hamiltonian of a peaked wave function, and that is what getting you the classical dynamics. But in the case of
in a standard collapse theory for a particle, actually two interesting things happen. When the particle is extremely delocalized, the degree of delocalization is large. One very important thing that will happen is that the collapse will change the thing dramatically. In the GRW thing, it very quickly localizes to something of the order of well, not very quickly, but when it does localize, it localizes to something of the order of 10 to the minus 5 centimeters. So if your particle was spread over, you know, kilometers, and then of course, if you have a free particle, we know that the wave function tends to spread again. So it spreads for more, until another collapse happens. So the particle is constantly doing, and supposedly the path of one particle really is not going to be affected too much, because the collapses in that case happen every once in a while. But once you have a microscopic object and you have 10 to the 23 particles that are entangled, then it's enough that of one of them to collapse. And then a macroscopic object will follow something like a very, very close to a classical trajectory with little wiggles like that are the interplay of the widening of the wave function natural of standard of quantum mechanics plus the rapid plus the collapse. So you will get really classical wave functions for objects that are large, that contains many degrees of freedom, and not and for a single particle, you know, you have.
Yeah,
sorry.
So this is the thing that I don't see how you get back in the case of general relativity. So in the
well, no, the idea here in the semi-classical approach that we are dealing with, matter plays a very important role. The thing that is subject to collapse is the matter fields, which is the part that is being treated quantum mechanically. Okay, in our scheme, if there was vacuum, there would be no collapses.
So the matter content is it subject to some Hamiltonian constraint or something? Or?
The matter content is described in terms of, let's say, the matter fields of the standard model. So
right,
that's
with
and if you have an inflaton,
so
put it together. If you have an inflaton or dark matter particles, you will put them also and do field theory for them and do quantum field theory in curved space-time, and they will be treated quantum mechanically.
So the matter degrees of freedom evolve because they are not subject to a Hamiltonian constraint or anything like that.
No, the whole thing is subject to a Hamiltonian constraint. The Hamiltonian constraint involves both the gravitational and the matter degrees of freedom. But the matter degrees of freedom the evolution for them is not the standard Schrodinger evolution, but the Schrodinger evolution corrected with this collapse term, right? And then, sorry, perhaps I went too quickly. I'm sure I went too quickly. But it's this equation, right? So here the first, okay, this Schrodinger equation, the first part is the standard part, the Hamiltonian constraint, and this CO and CA are the constraints that involve also the matter fields. They are the expressions for, let's say, rho and J of which are quantum, are written in terms of these matter fields, and of course the method probably plays a role there, covariant derivatives, and so forth. And then there is this other term, which is written in terms of the degrees of freedom, some of them which are being treated classically, like H, some of which are treated quantum mechanically, which is, well, here I did the quantum version, so here is supposed to be a quantum version, sorry. And so everything is quantum mechanic, but the thing that is going to be subject to collapse is the matter fields. The part that is going to affect the thing are the matter fields. Because, the question is one question that is open into this whole program is exactly what is the collapse operator? In the case of non-relativistic quantum mechanics, the people that have worked on this theory have chosen this smear position operator. But the position operator is not a good operator in quantum field theory. Okay, so we need something else, something that will reduce at effective level to the smear position operator, but will have to be something that is written in terms of quantum field theory in curved spacetime. Now, what is that operator? Okay, we think that something like extracted from the energy momentum tensor is the right thing to do. But then you, of course, want the thing to be covariant, and then you're likely to try to write a scalar out of that. One possibility is, the simplest possibility is the trace of the energy momentum tensor, which is a scalar. But it's not obvious. You can perhaps contract the energy momentum tensor with itself. I don't know. There are zillion possibilities, and we don't know yet what to do. Of course, that all that thing becomes even more complicated because those operators are not only singular and they need to be renormalized. So the whole thing is a messy issue. But
okay, thank you.
Okay, so Bruno.
Yeah, thank you. So just a curiosity here. So in that model where the collapse rate is tied to the Weyl curvature, we expect that in the early universe, this collapse rate was going to be small and the dynamics. So when you go back to that equation for the problem of time, you would expect that time would be almost disappearing at the early universe. Is this a desirable feature? That's my question.
That's a very, very good question. And I don't know if it's desirable. I certainly want some time happening because I want something to take us from the early universe to today. Now I don't know, to what degree time. I mean, if time is going to be emergent and it's going to be cumulative, perhaps our intuitive notion of passage of time will be modified under those conditions, but this is a very good question. It for sure, it better not be the case that the thing vanishes completely, because then we would, if this story is correct, then we would have nothing to take us from the early universe to today. But it perhaps is more sparse than it's, that is in the world that will happen.
I think it's not even obvious to have a time and a rapid rate of change on anything. The connection is not so straightforward anyway.
Yeah.
Thank you.
Yeah, thank you for the question. It's a very good question.
Are there other questions? Alvaro?
Yeah, if I may, it's just a small thing. You mentioned that there is a violation of the conservation of energy in any reasonable solution of the measurement problem, something like that. do you include Everett in reasonable interpretation solution of the Schrodinger problem?
Even Everett. Yeah. In this work with Tim Modlin and Elias Apon, we revised the three paths that I mentioned. Bohmian mechanics, where you can see it actually very straightforward, exactly what it is. Collapse theories, where it's well known, and actually there are, many of the tests of the empirical tests and bounds that are being set on the theory are obtained by precisely looking at self-heating of things like Bose-Einstein condensates. And in the case of many worlds interpretation, you can argue that in the collection of all branches that make out the many world universe, there would be energy momentum conservation. But in each one of the individual branches, if you concentrate in each one of the individual branches, there would be variation of energy momentum conservation. And of course, what we are supposed to experience in our world is one branch. So in our branch, there would be a variation of energy momentum conservation.
Oh, okay. Thank you.
You're welcome.
I have just a curiosity. So you talked about possible scenarios and possible applications at the cosmological scale, but I'm curious about black holes. And in particular, I would like to know whether you have worked or you plan to work on black holes, and in particular, whether your approach deals with what in some approaches to quantum gravity is called well, it's a very specific region phenomenon. I don't know how to call it in a sense, which is asymptotic silence. And if yes, considering your picture, what's the way in which you treat it?
Yeah, okay. In my particular work, I try to be very agnostic about what quantum gravity is. I don't know what the quantum gravity is, and I don't have a theory of quantum gravity.
Nobody has.
Okay. So the idea here is to say, I'm going to modify, and sorry, there's several, in these works, we treat these problems specifically, the black hole evaporation and loss of information problem. These papers in this RevD are actual, concrete calculations of this thing. But the calculation is based on a certain assumptions. So the assumption is that the quantum gravity region removes the singularity and removes the need to put a boundary here. And moreover, even though there will be violations of energy momentum conservation, we argue, or we assume, that they will not be very, very gross. And therefore, since most of the energy in this picture that was present in the black hole is present here in the form of Hawking radiation that has gone to Scribe plus, to asymptotic infinity, there would be very, very little energy left on this region. And then the assumption is that you have here at the end, after the quantum gravity region is gone, if you want, after the wave has broken in the ocean, after this region that you don't know how to describe, the smoothest possible simplest possible space-time compatible with the fact that there is almost no energy. And that would be something like a vacuum. So in our analysis, we basically put, Minkowski vacuum or Minkowski space-time together with the vacuum state for this region. And of course, a thermal, the Hawking thermal bath that is going to be present here. Okay, but we do not know how to deal with that, and we do not attempt to deal with that. So I don't know if that answers you.
Well, yes, in reality, you answered that. Even if it would be interesting to look at what happens, let's say, at sigma 4 and epsilon p, where the arrows points to that intersection.
Yeah, those are those, of course, but for that you need for sigma p in particular, you need a quantum theory of gravity. We recently wrote a paper in which we discuss the pros and benefits, the pros and cons of this picture that I have presented here, and contrasted with a picture that has many similarities, but some very important difference that emerges from the program of loop quantum gravity. Alejandro Perez is a researcher in loop quantum gravity, and we wrote together with him this paper that is, published in this book honoring Penrose's Nobel Prize, in which we contrast the two views, and it turns out there are some things that are similar in the two approaches, in which in the approach that I favor, we have this collapse theory, removing the information. In his picture, he has some remaining defects that remain after the black hole evaporates that involve quantum gravity degrees of freedom that are not represented by metric, are not representable in metric terms in standard geometrical language that encode the information that remains here. So the two stories are very different. The pictures are very similar. And if you want, in his picture, you have this region playing a very important role of converting degrees of excitation of the degrees of freedom that were in the form of excitations of matter fields in this part into this excitation of these defects that in the loop quantum gravity program would appear and emerge to the other side of the story. So you're right, if you have a theory of quantum gravity, a preferred theory, you can try to complement this picture.
Well, thank you. So I have there is somebody else. So Lorenzo Maccone, please go ahead.
Yes, I have a question. I'm sorry, I had to leave during the discussion. So if somebody already asked something like this, please ignore my question. Anyway, you are using this canonical approach to quantum gravity, which, as you said, requires global hyperbolicity. But then you are considering situations like black hole evaporation, in which you pointed out is not. There's not a Cauchy surface because of the singularity, and there are also other situations where. Right.
So let me clarify. So yes. Again, the standard picture like this is the one that doesn't have Cauchy hypersurfaces, because there is this either singularity, or you could try to remove the singularity and put a boundary of space-time just before the singularity or something like that. Anyway, this picture, if this is the picture, there is no Cauchy hypersurfaces, but also no information loss problem, because there is no reason whatsoever that information that was codified in a hypersurface here would be codified equally on the hypersurface here. Unitary evolution would only be predicated according to standard quantum mechanics without a collapse theory for full data on a Cauchy hypersurface connecting to full data on another Cauchy hypersurface. Okay, so there is in that case. So if we have this picture, there is no information loss paradox. There is information loss paradox if you assume that quantum gravity cures the singularity and removes. So this is a different picture. This is a picture in which there are Cauchy hypersurfaces, in which there is a region where some quantum gravity, which I don't know what it is removing the singularity and replacing it by something that is not singular. Okay, but that nevertheless allows you to talk about the future of this region and the past of this region in such a way that sigma 1 would be a Cauchy hypersurface and sigma 2 would be a Cauchy hypersurface. And it's in this context that
Yes.
we argue
Okay.
that collapse theories will help you deal with the black hole information problem. Because if this is the picture, now you have a problem.
Yes.
If you have just the standard unitary evolution, then you have a problem, because you have sigma 1, perhaps a pure state, and sigma 3, you have, well, this state of an entangled Hawking radiation, entangled with degrees of freedom that are in the interior region. And then you don't have any good thing. Normally, you don't have any good thing, although Alejandro has, to put here on sigma 2 to be entangled with the states of sigma on scribe plus to make this state pure. That's the measure, the black hole information problem in a short sense, right? But our point is that since we deviate from unitary evolution, then I have a way to account for how this state that was pure here went to this other state where much less information is present.
Yes, yes. But what about the other space-times which are not globally hyperbolic? I mean, in general,
space-times that are not globally hyperbolic, I don't think there would be any. There is no. I don't see any information.
No, but a canonical quantum gravity approach will not be able to treat them, right?
Well, I don't know what the quantum gravity theory would be able to do, but if it uses a canonical approach, if in those things there is loss of information, I would be not surprised at all, and I would argue there is no problem. Your thesis is not global. Let's take Gödel's universe.
Yes. Sorry.
Gödel's universe.
My question
I would say, well, there is no.
No, I agree with that. But my question was another one. How can you treat those situations? You cannot, because you're using just the canonical approach to quantum gravity. So you cannot deal with spacetimes which are non-globally hyperbolic, right? But those are present. Those are in.
Yeah, look, I'm not even doing that. I'm not even treating. You see, I didn't even go all the way to do quantum gravity. I told you that in the semi-classical picture already, this feature will help you account for these features without having to get into the details of how quantum gravity operates. And the specific questions that I asked were, can I address how, seeds of cosmic structure occur in inflation? Can I address the black hole information problem? What lessons do I learn from that at the level of which I'm talking, which is a very effective level of semi-classical gravity, which I regard as an effective characterization, which still lacks.
I guess my question refers to the Kerr black hole solution, for example, where you can get closed time-like curves, and then you will not be able to treat those, right?
Well, in the region where you're going to start getting closed time-like curves is also the region which has passed the Cauchy horizon, and then you already in some sense in contact with the singularities, and then quantum gravity effects will play a role. I don't know what gravity is, but they should certainly be in causal contact with that region where you could have the time-like curves, right?
Well, I'm not so sure, because those regions are pretty extended. They're not. I mean, they're connected to the disk singularity, but they're not like Schwarz.
No. The singularity in the first of all, that's number one. That's the vacuum. That's the vacuum eternal Kerr solution that you're talking about, right? That's not the solution that is produced by gravitational collapse.
Okay.
Right. You're talking about the standard Kerr.
Yes. I'm talking
right,
about
which refers to an eternal
yes,
black hole that has existed always, and So that you know.
You say that this is not physical. That's what you.
Well, even if it's not physical, one should be able to ask questions, but it's not something that I could say, let me put this state here and there is information encoded in the matter here that is going to fall and blah, blah, blah. If I'm going to do that, something of that form and put quantum fields falling and producing the black hole, which is the normal way in which information paradox arises, I will not be using that picture, right?
Yes, yes, yes. No, I was not specifically talking about the information paradox. I was,
Yeah, I know. Well, what generically would be of an eternal, what generically would be the fate of the eternal Kerr solution in a quantum gravity theory? I'm sorry, that was.
Yeah. Okay, thanks. Thank you. Yeah, thank you.
Okay, so if there are no other questions, we can thank our speaker. Thank you very much, Daniel. It was a pleasure to have you, and see you all in a week time for Valia Lori's talk. Thank you very much, and see you soon.
Thanks. It was very, very interesting. Thank you.